we have more people here. So let me introduce Patrick. Patrick is a Colombian and French solar physicist, and he's working at Northumbrian University. I apologize for probably mispronouncing the name. So Patrick's research career had been a roller coaster. His PhD studies in solar and astrophysics were conducted in Kyoto, Japan, and Oslo, Norway, with Kazunari Shibata and Mats Carlsson, and he graduated in 2012. He then moved to Belgium to work with Tongwan Darcelare, and then back to Japan, to the University of Tokyo to work with Taki Yokoyama, and then he worked at National Astrophysical Observatory of Japan in Tokyo, in Hinode team. Then in 2016, he moved to Scotland to work with the Naked Immortal. Before finally he moved to in 2019, he moved to Newcastle with a Rutherford Fellowship, and he's a senior lecturership. He got a senior lecturership at Northumbria University. Patrick is interested in observations and simulations of events within the inner solar corona that are associated with coronal heating, such as MHD waves and magnetic reconnection, and also such as cooling, such as coronal rains and prominence. And with that, I give this into Patrick.
Okay, so hello everybody. Good morning, good afternoon, good evening, from wherever you're tuning in around the world. Thank you very much, Anna. Thank you very much, HAO, for inviting me to give this talk at your online colloquium. It's always a pleasure to talk about this topic for me. So I'm going to talk about kind of the dark side of the solar corona today, a side that we have known to be there for a long time, but actually is still very poorly known. So it's kind of the cool side, and that's why it's, I gave it this name. It's the thermally unstable solar atmosphere. But it has to do more about cooling than heating. So this is the outline of my talk. So I'll mention a few of the very puzzling features that we observe from the hot solar corona. These are the features that have been driving the field over the last 70 years. And in particular, I will talk about coronal loops, which are the basic constituents of the solar corona. And then I'll concentrate then on the cooling signatures that we see in the solar corona, and in particular, coronal rain. And prominences are of course included here, but coronal rain really deserves the biggest credit here. And I'll show what are the observed properties of this phenomenon, the three flavors that we see of this phenomenon: quiescent, prominence, hybrids, and flare-driven. I will show some new observations that we have of solar orbiter with the EUI instrument of coronal rain. And then I'll focus on the mechanisms, which are thermal instability and thermal non-equilibrium. So the mechanisms that we think are driving this phenomenon. I will also show some numerical results, what we have learned from multidimensional simulations especially. And if I have time, I will show analog phenomena at much larger scales in the universe before concluding. So let's start our talk today with one of these fascinating movies that AIA gives us every day of the solar corona. So here we are seeing the 171 channel, which is pretty much 1 million degree Kelvin. And we immediately see that the corona is very filamentary in this temperature. It's composed of these open and closed, especially flux tubes. So the closed flux tubes are within what we call the inner solar corona, and they are very hot, right? So they have several peculiar features, which I'll go through. But now we have a very good understanding of where the energy comes from, right? So of course, these are from the inner layers of the solar atmosphere. So if we look at what is happening on the photospheric level or at the chronospheric level, right, we have these magnetoconvective processes underneath the photosphere that are driving these granulational patterns. So these are constantly stressing the magnetic field lines, so constantly injecting energy, and then the magnetic field is then basically charged up with energy. So we are able to measure quite well the energy that goes into the magnetic field through these buffeting motions. And the picture that we have of the solar corona is a bit like this, in which we have these magnetic elements that are expanding because of the change of the density with height, and then the corona is magnetically dominated, and we have a very large pointing flux going into the upper layers. So we do not know how much actually of the pointing flux that is at the photosphere reaches so far into the corona, and that's one of the biggest problems. So the energy then gets transformed somehow into heat. So the plasma gets rapidly ionized and then heated, and then we have the formation of the corona. Right. So 70 plus years of research have indicated that we have two big camps of heating mechanisms that we roughly categorize as MHD waves and stress-induced magnetic reconnection, which differs on how the energy is injected on the spatial and temporal scales of the energy injection. And then given some dissipation mechanisms, each one of these groups will dissipate differently the energy in the upper layers in the corona. So of course, we do not know what is dominant, and that's what this is all about, detecting also these coronal heating mechanisms. So these loops are very puzzling for several reasons. So we would expect loops that are kind of hydrostatic, like imbalance with their environment. That this is very far from the truth. They are often overdense, particularly in inactive regions where we can see them. They show always cooling, so there's widespread cooling everywhere. And a good example of that kind of research is that conducted by Vial and Klimchuk over the last decade. And then when we tune the temperature that we're seeing, changing the spectral line with an instrument such as the ice, and we go from several million Kelvin to million Kelvin and even below million Kelvin to transition region temperatures and even chromospheric temperatures, we see a very big change of the morphology of the solar atmosphere. So it is very filamentary, as this series of movies show. And also, apart from becoming filamentary, it is becoming also more variable. So the EUV variability that you see here is on time scales that are lower than 1 hour. So we're talking about tens of minutes. And of course, the problem here is that although we see cooling everywhere, we do not see the heating. We're not able to see on average the heating events, the small scale heating events, because these they occur on very short time and length scales in coronal lines, in the hot lines, for which we do not have the resolution yet, and for which also the coronal magnetic field is highly uncertain. The topology, of course, is invisible directly to us. So another very puzzling feature is the structure of coronal loops. Right? So with the development of instrumentation, with the increase of spatial resolution, we are able to probe with instruments such as HIC and now Solar Orbiter EUI, what we call the substructure of coronal loops, right? And we see strands, what is called the strands. And the question here is whether these strands correspond to the spatial scales of energy transport, the kind of fundamental spatial scales in the solar corona. Also, another peculiar feature is that these loops and the constituents, the coronal strands, do not show any constant cross-section. Do not show an expansion as expected. So they show a constant cross-section with height, right? And this has been strongly debated. And for example, Anna Malamchenko has shown a possible explanation for this, which is based on basically the optically thin radiation of the solar corona. So here, the scales that we're talking about are of a few hundred kilometers, right? So these are the smallest scales that we can currently resolve in coronal with coronal instruments. So we also, through the last decades, we have noticed that the loops are also variable in the flows that they host, and we see often downflows across that are multithermal, right? So from chromospheric, also transition region lines, in active regions, we see downflows quite often, and these can be strongly redshifted, even shocked, produce UV or UV bright points, and they're sometimes associated with some outflows. So above sunspots, the morphologies that they have is that of plumes, so like plume-like structure. And one of the a big mystery that has recently been solved is actually that these downflows sometimes last for several hours, right? So this is corresponds to significant mass flow, corresponding that if the loop is closed to begin with, and so we're talking about mass flows that are far more than what is presumably contained in the coronal loop at the beginning. So this has been a puzzle. Then another example of the UV variability is the so-called long-period UV intensity pulsations. So this is another very peculiar phenomenon that we see with in the AAA passbands, before with EIT as well. There are bundles of coronal loops, or even in the quiet sun, that show periodic intensity variation across almost all the AAA passbands. So basically multithermal. And these are typically have very long periods, between 2 hours to 14, 15, 16 hours. And the limits are just ad hoc. So we do not know how short they can be. We do not know how long they can be. And also periodic UV flows have been associated with these pulsations. So here the biggest question, I mean, if they have a similar intensity, so we tend to think that this is a similar thermodynamic evolution, and therefore the question here is, how can a region like a loop, like we can see here in this example, maintain the same heating profile that would lead to the same thermodynamic evolution over several days, given the stochastic nature of the solar atmosphere? That's a big conundrum recently in solar physics. So here I've placed several questions so far. So why does the corona appear more filamentary in cool transition region lines? What defines the cross-field structure of coronal loops? How are these long-lived multithermal and dense downflows produced? And how can a region maintain the same heating profile over several days given the stochastic nature of the solar atmosphere? So in order to answer some of these questions or shed light significantly into them, we need to look at the cool plasma of the solar corona. So over the last decades, and starting from the NCAR archive, we know, maybe you can hear the music as well, but we know that the existence of these loops, well, with cool material of tens of thousands of Kelvin or below, basically everywhere in active regions, and in particular after flares, right? So this is an archive from the 50s. So we know that it's there, but it's only recently that we have realized how important this cool material is, and how strong is the link between the presence of this cool material and the hot material at the end of the solar atmosphere. So there are several flavors of this cool material. They do not all fall in the same category. The most famous ones are, of course, the prominences, because they have a big impact on Earth, or the flare-driven coronal rain that usually follows flares. But there are also two other kinds, which are referred to quiescent coronal rain, which is the one that appears over active regions, and it's by far the most common of them. And more recently is one that is more strongly associated with prominences. So that's why it's called a hybrid prominence coronal rain structure. So the properties of this cool material, in particular coronal rain, is that it's cool, of course, and dense. I'll give numbers in a bit. That is ubiquitous in active regions. You check any active region with AIA 304, you will see coronal rain. It's dynamic and multi-thermal, very dynamic, as you can see in this movie. And it comes in like very different shapes, but it's mostly clumpy, stranded, so it's filamentary in that sense. And also there are like groups of clumps that we refer to as showers. So there's also many questions around this. What is the formation mechanism? How much coronal rain is there in the solar atmosphere at any given time? Why is it clumpy and multi-stranded? What role does it play in the solar atmosphere? So there have been several studies performed with ground-based and space-based instrumentation aimed at properly measuring all the properties of coronal rain. So now we know that the temperatures are quite broadly distributed, but they peak usually around 10,000 Kelvin for the material that is observed with H-alpha. So, and these correspond to the smallest clumps, but it has a long tail above towards higher temperatures that we can observe with other instrumentation. So IRIS has contributed a lot into determining how multi-thermal this coronal rain is. So we usually see it also up to 10 power 5.5 K. So it's also as much a transition region phenomenon as it is chronospheric, or even more. The densities are quite large, as you can see here in this histogram. So these are total number densities, and it's usually between 10 to the 10 and 10 to the 11. It can be up to 10 to the 13 for flares. So because of these very high densities, it plays a big role in the solar atmospheric, what is referred to as the solar atmospheric mass and energy cycle. So talking about closed loop structures here. But not everything is closed, and now we know that there are quite some counterparts to these that are perhaps much more extended in the solar atmosphere. So not only they can link active regions to other active regions, or just an active region with a quiet sun, but you can find them at very different latitudes, and these are the ones that are called hybrid prominence coronal rain complexes. So here, Li et al. And colleagues in China have shown that we often see this kind of topology in which we have an closed arcade below, and an arcade that can be either closed or open above. So you have the formation of a magnetic dip. You have magnetic reconnection processes that appear there. So because you have a magnetic dip, the material can accumulate there and just condense, and they may play a very important role because of the very large mass reservoir, and because of the probable connectivity with the solar wind. They may play an important role also in solar wind and space weather effects. So these can be very long-lived. They have been a structure can be observed for up to 8 months. Because they're fairly new, there's a lot of questions that surround this sort of structure. So how common they are, for example, we do not know that. Now, another very interesting property of the coronal rain are the dynamics. And with spectroscopic instruments, we're able to measure the total velocity. So that's using the plane of the sky motion and the line of sight, so the Doppler and imaging. And the velocities that we observe are often below 100 kilometers per second, so peaking at the 70, 80 kilometers per second, but with a very, very broad velocity distribution, as you can see in these histograms. And the acceleration that these clumps exhibit as they fall towards the solar surface is often very, very small, much lower than free fall, and even much lower than the effective gravity, taking into account the geometry of these coronal loops. So that points to the existence of other forces besides gravity, and now we know that gas pressure force can be dominant and can explain this kind of velocities. So here you can see a map on the right-hand side of the projected velocities, and we see some acceleration towards the lower heights, but very rapidly this acceleration stops and they fall at around constant velocity also. So what happens? What can explain this? For that, some numerical simulations have been run, so in 1D and 2D, and what happens there is that when you have a clump, so that you have basically a density enhancement that is produced in a timescale of minutes in the solar corona, the environment reacts very rapidly to that. So basically, it launches sound waves upstream and downstream from the magnetic field lines. Telling the plasma that that something is coming, basically. So you have a restructuring of the gas pressure downstream, as you can see in this movie here, and that basically falls down immediately. Decelerates immediately the coronal ray. And if you plot the maximum velocity versus the density ratio, you obtain a relation that shows this. So here you should look at the black dots, a relation that is very, very well defined. So it's a factor of 0.64, and we do not know why this is, but we suspect that this has to. I mean, this is a hydrodynamic effect, but in an MHD environment. So it's something that happens in a coronal loop that can be explained in a 1D HD simulation. So here there's some analysis that needs to be done mathematically that in order to show why we have this relation here. So now on the morphology, so we have this very peculiar multi-stranded and clumpy morphology. So when we talk about multi-stranded or filamentary, we often refer to the morphology that this material shows perpendicular to the flow. So that means perpendicular to the magnetic field, while clumpy refers to the other direction, right? So the longitudinal direction along the flow. And we know that it's very different, right? So the lengths that we get in on both are very different, and there have been a series of possibilities to explain that, and I'll talk about this in a bit. So this multi-stranded, particularly the multi-stranded component, it's on the order of a few hundred kilometers. So here, if you see the graph on the right, so you have several measurements in different lines, in different temperatures, but also in different with different spatial resolution. And what you see is that, well, for higher spatial resolution, we will go down on the width. So this is the size of this rain clumps, the width of the rain clumps, up to a few hundred kilometers. And interestingly, so this matches quite well the smallest sizes we can currently detect with instruments such as HIC and Solar Orbiter. And the question then is whether there is any relation at all, or if this is just a just a casual. It happened to be the same. So a possibility has been proposed, so that it's shown in this sketch, in which the clumps, the cores, the very cool cores that we see, for example, in H-alpha, should be surrounded by a sheath of strongly emitting material at transition region temperatures before, so in the surrounding corona. Right? So this transition between the corona and the chromosphere should be very thin, but very strongly emitting, like as the normal transition region is. And therefore, that would explain why we would see this the same kind of EUV widths for the loops that show rain, right? So, of course, these are not all the loops that we see. And then in this picture, Solar Orbiter can kind of provide can be very complementary, and that's because we can see the coronal rain at very high resolution. We can see it in absorption. So this is a very recent Solar Orbiter observation. So this is from the last perihelion in March. So this is the highest resolution that we have had so far of the EUV solar corona. And here, this is a coronal rain event, and you can see the material in absorption falling, and you see the groups of clumps. And here on the left, I show one snapshot of a clump, which is the dark feature here, and you can see that it's barely 2 pixels wide. So we are recovering the same kind of morphology that we can see with H-alpha, which actually was expected from the studies by, for example, Anther and Heinze. There should be a very good correspondence between the two. But also, we can see other very interesting features. As the clump falls, we can see the compression of the plasma underneath. If you have a sharp eye, you will see that if you catch one of these clumps falling, you'll see that underneath it shows a bright region. And then following this, the impact from the rain, you have an increase in intensity. Basically, you have a rebound shock and a wave propagating upwards, and so enhancing and reheating the coronal loop, enhancing intensity. So we can measure the velocities in the plane of the sky, and they correspond very well to the velocities that are expected from coronal rain. So these are those that you can see here in this histogram. So looking at 50, 60 kilometers per second in the plane of the sky. And the velocities that you can see here that are negative actually correspond to the rebound feature. So this feature here that is bright in this time distance diagram following one of the paths. So you can see that it either shows 50 kilometers per second components to 130 kilometers per second components. And this very likely is the combination of a flow and a wave that is propagating upwards. And that's why we have this very large difference depending on where you take the path. So the upward speeds that we get are the maximum upward speeds match the tube speed that is expected at this temperature. And if we take if you do similarly this type of time distance diagrams for several paths here that I have number 1 to 10, you can see the features here of coronal rain, so the EUV absorption slopes, all basically in all of them, and roughly at the same time. So this is what we call a shower, and that I will talk in a bit. Yeah. So showers. So actually, the clumps that you have seen, they do not occur in isolation. They often occur in groups, and often it's a bunch of very close, neighboring clumps that you see happening at the same time, and they follow a similar trajectory, and therefore that gives the name of shower, right? So shower is then the group of clumps that we see that occur roughly at the same time and follow a similar trajectory. And we have noticed that actually the widths of these showers, they match very well the cooling coronal structures that we can, those that we can easily identify in the plane of the sky. So basically, the showers, in that sense, they help identify the loops in the so-called coronal veil, as I would call it. And so the question here is what establishes this coherency, right? So because this is cross-field information somehow. I mean, is this just serendipitous, occurrence of coronal rain, or is there something else? Is there a sensing mechanism across the field bands? Before talking about all these mechanisms, I will talk a little bit about the flare-driven rain. And the flare-driven rain is the mechanism where we really see the accelerated cooling that is happening in coronal rain. So in this example by Scullin et al. In 2016, you have C-class flare, right? So you can see the intensity, the usual trend of the intensity following the peak. So that's the gradual phase of the flare. Where we expect conductive cooling to dominate and then radiative cooling to dominate. So we can follow the trend in the intensity across the SDO channels, and then at the very end we have, in this observation, we have a CRISP. So CRISP is a spectropolarimeter, imaging spectropolarimeter at the SST that observes here in H alpha in this case, and you can see that there is here is again 10,000, roughly 10,000 K, and you can see then that there is an accelerated cooling phase at the very end. Right. So here it's worth to mention, to recall how does, what is the flare scenario, right? So in the standard flare scenario, we have reconnection happening somewhere in the corona. That so the prime energy transport mechanism at the beginning of the flare is thought to be the accelerated electron beams that would transport the energy from the corona to the chromosphere, leading to the chromospheric evaporation, the heating, and the formation of the flare loops. So these are the ones that we see with SXT. And then the cooling starts, and very rapidly, depending on the density, it goes down to 10,000 K or so, and then we have the H alpha loops, or that we can see here in this movie. Right. So, and the question is, well, how is really coronal rain produced? Is it the same kind as the quiescent coronal rain? A very interesting observation of flare-driven rain was done by Jing et al. In 2016. So this is again on disk, and you can see at the beginning of the event, you can see the ribbon. So this is the location of where the electron beams impact on the solar chromosphere, and tens of minutes afterwards, you have the coronal rain following the same path. So basically, scanning again the same path that the ribbon has shown in the beginning, and the width of the ribbon in H alpha, as you can see here, matches very well the width of the rain that we can see in absorption in this case. So this suggests that we have that the rain is basically showing the true spatial scale of energy transport in this kind of flares, and therefore it would match also the hypothesis that we did before of whether the width that we see for quiescent coronal rain. Why would it match the widths that we see with in UV? But how is flare-driven rain produced? And it's peculiar. It's very interesting to notice that we have an atmospheric response to cooling that seems proportional to the heating, right? At first, so that's the first thought that we have about this. That the more you heat, the more it cools and rains. And of course, there are limitations of this that we need to explore. So now about the formation mechanisms. And here we need to talk about thermal instability. So I have been beating around the bush too much. And here, in order to understand all these phenomena, we need to understand thermal instability. So thermal instability is the instability of the thermal mode. So that's an MHD mode, and that is obtained when you have non-adiabatic losses. So if you do the perturbation analysis on your MHD equations, but include the non-adiabatic terms such as radiative cooling, optically thin radiative cooling, thermal conduction, then you reach very interesting formula that I have shown here on the right. It's a three-order polynomial. So it has three solutions, and one of them is the thermal mode, and the two other ones are acoustic modes. So Parker and the field in the 50s and 60s showed that when you include these non-adiabatic effects, the thermal mode can become unstable. And how does it look like? Well, it corresponds to a non-propagative density enhancement. And the way you can have this instability is, well, whenever is basically the cooling is thermal conduction always tries to kill the cooling, right? So thermal conduction has the job of distributing the heat in coronal loops. So you can have an instability, a thermal instability, whenever the thermal conduction is not efficient at transporting this energy. And then this then depends on the wavelength of your perturbation, of the thermal perturbation. And if it's larger than what is called the field's length, then well, very likely you have instability. And you can do analysis, like Kless and Keppens have shown this in the last few years, that so here this is just an example, taking just normal parameters of the solar corona, and you calculate the growth rate for the thermal mode, for the slow mode, for the fast mode, and always is the thermal mode is the one that is most of the time unstable. So these are the values that are positive in this graph of growth rate versus temperature. And when taking a Valsy atmosphere, you will always have in the lower layers of the atmosphere wavelengths of the perturbation for the perturbation for which your plasma is thermally unstable. So very likely, I mean, what this suggests is that the chromosphere, the lower atmosphere, is very prone to thermal instability, and this needs to be explored in much more detail. So an example of thermal instability has been applied from the very beginning to prominence formation. And this is shown here in this example by Xia et al. 2011, in which you have a very long loop with a small dip. So just this is the shape, so that you can have accumulation of material here. And if you do the time distance diagram along this loop, you'll notice that so this is the time distance for different quantities, and you notice that the temperature very rapidly, catastrophically cools down at the very end, and this is when thermal instability happens. So when that happens, you have a formation of a density enhancement that is shown here. So this is the thermal mode becoming unstable, and well, these are just details that you don't need to know. But this has been since been expanded to multidimensional simulations, such as the one of Mouchou et al. And the locations where we have coronal rain match very well the locations that are unstable, in which the thermal mode is unstable. Now the question is then, how is thermal instability achieved in a coronal loop? And for that, I show a very typical example that is often done in 1D. If you take for your energy equation an energy that has a heating component DH, that is strongly concentrated at the foot points, so known as stratified or foot point heating, so with an exponential decay with height and just constant to make it simple, you will see cycles of heating and cooling as shown here in the time distance diagram, and here this is the movie corresponding to this. So here, so you have cycles of heating that you can see. So forget about this first part. So this is just due to the initial condition of this simulation. We have a heating and then followed by a cooling where you have coronal rain. So this is what we refer to as thermal non-equilibrium. So this is the inability of a loop to reach an equilibrium state, and that is because of the spatial and the temporal distribution of the heating. So so this is shown in this sketch here, where you have on the one side you have coronal heating events that are distributed somewhere in the corona, but in the low corona especially. These are from thermal conduction transferred very rapidly downwards, and you have chromospheric evaporation. So your loop becomes very dense rapidly, and then it starts radiating very efficiently. And then in the appropriate conditions given by stratified heating and high frequency that have been quantified by Kimchuk and Luna, then you have loss. So you have an unstable. So you have radiative losses that are dominating the corona here over thermal conduction, and that's where thermal instability takes place. You have the condensations forming; either they accumulate in the corona to form prominences, or they fall down as coronal rain. So the parameter space in which you can have this combined thermal non-equilibrium and thermal instability process is very broad. Right? There are many parameters that can change how these limit cycles are produced. You have the heating stratification that I talked about. You have the event frequency. You have the stochasticity of the events, what we call the background heating. So the mild heating that is happening, but we do not know where it comes from. You have area expansion. You have the loop length, the radiative cooling function, the details of the radiative cooling function, the heating and area asymmetries between the foot points, all can change the limit cycles. So in a way, it's very sensitive to these parameters. And that makes it both very complex and hard to investigate, but also very interesting to explore. So now we can explain the phenomena like UV pulsations. And this has been the work done by Clara Froment over the last 7 years or so, in which she shows with numerical simulations and observations that these TNE-TI cycles match very well the observations of the UV pulsations. So in a way, the intensity pulsations that we see in the EUV correspond to the large scale, the long duration of this process, while the coronal rain that's visible in the visible spectrum or UV spectrum corresponds to the short scales and fast duration. And now we have observed periodic coronal rain in each one of these cycles. So this is a solved problem. And we can say that coronal rain and non-periodic intensity pulsations are two sides of the same coin. But how can the same heating profile be maintained over several days despite the stochastic nature of the solar atmosphere? That's still a question we need to solve. So the rain shower process that leads to rain showers may provide an explanation here, and this is known as sympathetic cooling. So in 2.5 dimensional MHD simulations, Fang et al., the Leuven group has shown that if you have a loop bundle that is heated with strong stratified heating and high frequency, just constant in time in this simulation, you have thermal instability happening somewhere very locally in the corona. But because the field lines neighboring this first thermally unstable field line have a very similar thermodynamic evolution, they will be critically stable. So you have a kind of avalanche effect from one side and the other in which you have the thermal instability, the thermal mode becoming unstable very rapidly, and that's why you see in a time scale of a minute or so at first the growth of the clump of the condensation, which then gets deformed because of many different processes. We have shear flows and different things. So, but all of this kind of falls at the same time, thereby defining the shower and explaining why we see a very similar width with the loop. So, in this sense, this sympathetic cooling can be a kind of a reset mechanism to maintain this TNE cycle periodicity, but this is just a hypothesis at this stage. We can use the showers to estimate the thermal non-equilibrium volume in an active region, and this has been done by a student of mine, Saray Shahin, and using the IRIS instrument. So this observation here of an active region, we can see how much coronal rain there is, and these are so each color corresponds to a different shower. So the color corresponds to time. So this is over 5.5 hours. And by measuring the morphology and the dynamics of this rain, we can approximate the volume that is involved in the rain, and therefore approximate the thermal equilibrium volume that is involved. And we reach values that correspond to 50% at least of the active region volume. And this is a lower estimate because of the low signal to noise that we get from this kind of observation. So the question is still open: how much thermal non-equilibrium volume we can find is involved in an active region. So this indicates that the strongly stratified and high frequency heating in an active region can be very common. So now about the flare-driven rain, the formation mechanism. And the question here is whether the standard flare model can explain rain. So if we see the relevant timescales in this process, so the conductive timescale, radiative timescale, free fall timescale, you'll note that the radiative timescale is always much slower than the other two. And therefore, this suggests that we can have thermal instability. Here again, the electron beam is thought to be the main heating transport mechanism, and so this formula here is very complicated, but basically captures where the energy is deposited by the electron beam in the atmosphere. And what is important here is to note that this energy deposition goes with the density, the column density, to the minus a power, some kind of power. So it's a function of the column density. And the problem then that we face is that this initially foot point heating becomes very rapidly an apex heating because of the very strong chromospheric evaporation that we get. So the column density increases, and therefore the deposition of the electron beam then rapidly increases with height. And then if you do time distance diagrams, as shown here, you have a collapse of the corona, but no formation of the coronal rain. You don't have this characteristic increase in the density anywhere. And it's only when you add a secondary heating mechanism, for example, that is mild compared to the flare heating, but still important with respect to the quiescent kind of, to the normal coronal loops, that we get coronal rain, and only in very asymmetric conditions. So the question still is out there whether we need a secondary heating source or whether multidimensional effects can explain flare-driven rain. So now the last part that I would like to show is about some new numerical modeling of coronal rain in the 3D and 2.5D that is self-consistent. So now simulations with advanced state-of-the-art numerical codes such as Bifrost show coronal rain, and for example, Kohutova et al. In 2020 has shown this. But of course, when you do it in 3D, it's really difficult to capture the proper morphology of the rain, so the small widths and so forth. So we have extended that to 2.5D, but much higher resolution. So these are radiative MHD simulations with Bifrost. where we have quite a large corona. So again, self-consistent formation of the corona. And here, so you can see the details in this letter. So I focus on this. So if you look at a loop that shows coronal rain, and you plot the whole joule heating per unit volume, and the timescales of the heating, we find out that the conditions for thermal non-equilibrium are actually satisfied. So the ratio between the heating at the top and at the flood point is small enough to have thermal non-equilibrium, and also it's high frequency enough with little asymmetry. So we have the TNETI scenario here, and that therefore explains this coronal rain event. So here we have temperature, number, density, and several different quantities. So we have gas pressure, and importantly, we have the magnetic pressure here. And you will notice here that the magnetic pressure gets distorted when the thermal instability occurs. So why is that? That's because the field is still frozen in. So when you have a loss of pressure, you have basically a compression, radial compression of the material that leads to a small enhancement of the magnetic field. And that is small, but it's 1 to 2 Gauss. And importantly, it produces what is called a CCTR. So you have a chromosphere coronal transition region, and which then this can be considered kind of fundamental. So let me skip this. Let me skip this thing and just go to the interesting properties that we see as the rain falls. So during the fall, we have a very strong compression of the plasma. You have an increase of temperature to like transition region temperatures, a strong deceleration, and in the wake of the rain, you have a dense and warm tail. So and at all times, the ionization fraction in the rain is quite small, is quite high, the ionization fraction. So if we forward model this to lines like the A171 or the Iris silicon 4, we see plume-like structure that is formed below the rain, and the thin filamentary structure that's typical of coronal rain in the silicon 4 line of Iris. And therefore, this can explain why we see the same width, at least for the loops showing rain, the same width between the rain and the coronal strands. After the impact, so we also see the compression ahead of the rain. So this explains the observation of the solar orbiter as well. And we also get a rebound shock. So basically matching perfectly the observations. Let me skip this. So unfortunately, I need to skip this. I won't be able to talk about the phenomena, analog phenomena in the universe. So I'll just go directly to my conclusions. So we have these puzzling features of coronal loops around the morphology, of course the thermodynamics, the variability in the EUV, and we have learned that by studying the cool side of the corona, and in particular coronal rain, we can learn a lot about what is happening there in the hot side. So we know now that this cool material actually plays an important role in the mass and energy circulation. We have thermal instability happening with thermal non-equilibrium to explain these showers, and they are able to explain the EUV pulsations. The flare-driven coronal rain is still an open question. So we do not know whether we have a secondary mechanism happening here. The dynamics of coronal rain show that the gas pressure is very sensitive to rain dynamics are very sensitive to gas pressure. So in that sense, it's a proxy to what is happening internally in the loops. So we have a magnetic enhancement. And now we know that it plays a major role in the filamentary morphology and the UV variability of the solar corona. We know we have now numerical simulations that can consistently produce coronal rain, and then what this suggests is that the magnetoconvective processes are really the ones that are setting the scales of these fundamental strands. So we have the rain strands and the coronal widths. This should be linked to the granulation processes somehow. Right, and when we now know that thermal non-equilibrium can be prevalent over an active region, but we still need to more properly quantify how much of the solar atmosphere, in particular above an active region, is in a state of thermal non-equilibrium. I'll stop there. Thank you.
Thank you very much for the talk, Patrick. Do people have questions? We have time for a few questions. Well, I have a few questions of my own, actually. One question is, I'm kind of intrigued by the combination of concepts that, for one, is you did mention that the rain trace the width of a shower traces the width of loops, and you also mentioned that you made some estimates of how much volume in the active region is taken by the rain, and you found something like 50%. And at the same time, I mean, there are estimates of the volume fill-in factor for coronal loops, and it is small. It is like fractions of a percent. And I wonder how are those three things come together?
Yeah. So I think more precise measurements of this are needed. So we have through in particular Iris observations, and very likely with Dickies we'll have a much better picture of what is happening. But with Iris observations currently, we have a good idea of the amount of coronal rain that there is. So there the link is how to link the amount of coronal rain to the thermal non-equilibrium volume, and that is non-trivial. So there are several assumptions in that step that have been made. So for example, how much a shower is part of the loop. So you have a loop, and just part of that loop shows the shower, right? But it's the whole loop that is thermally it's in a state of thermal non-equilibrium. And then of course you have the question of the filling factor, as you have mentioned. So we have. So of course the rain also is not filling the loop, right? So we have this multi-stranded structure, and then we can only see the plane of the sky projection for the rain. So we make an assumption that the width in the plane of the sky is the same as the depth, right? But the strands that we see inside the loop will, they can be anywhere within that volume, within that 3D volume. So we can make estimates of the filling factor, probably placing upper value. I don't think that exercise has been done, but here we have only assumed, that we have a coronal loop that is the one that is showing the shower, so the thermal instability / thermal non-equilibrium event, and that's all, right? So that's the volume that we see. So that may be itself embedded in a much larger structure, like the what is referred as the loop bundle, the one that is assumed to show the expansion, that have the expansion. So how much of that shower, is part is with respect to that big bundle? I don't know. It's interesting to think about. But you can have different showers in the same loop bundle, of course. Yeah.
I wonder how do we even define a loop bundle.
Yeah. Yes. I don't know, but I mean, the observations at very high resolution with Solar Orbiter show that the showers can be very wide, up to 15 megameter, right? So that's much larger than what is usually assumed for a coronal loop.
Mm-hmm.
So maybe, yeah, maybe it can also tell us about the properties of the loop bundle. I don't know. Yeah.
Oh, thank you. There are some hands raised. So the first one chronological is Bettina.
Hello, my name is Vidina Shirgelashvili. I'm from Ilia State University, Georgia. Actually,
Okay, you hear me?
Hello?
Oh, okay.
You froze? Bettina?
We cannot hear you, Bettina.
Yeah, you started saying something and then you froze. Okay. Sorry. If you get back to us, let's for now turn to Phil and see if my Bettina has some connection issues that will get resolved.
Hi, Phil.
Yeah, thanks. This is Phil George. I'm sitting up here enjoying the outside tying flies in Colorado. So actually officially on vacation. So but I did enjoy your presentation. It's an awful lot of work. And without being in any way meaning to be rude or anything, I have two comments. One is, first of all, I don't believe the solar atmosphere is thermally unstable at all. I think that it does lead to things that are like coronal rain, but that occurs after pretty much a lot of stuff that's interesting has already happened. So for me, I see the corona and the transit and the chromosphere as two stable layers with rather long time scales associated with them for sustained heating. The chromosphere has to go through 9 pressure scale heights to even get to the corona. And so that indicates that it is a very stable looking thing. Secondly, the corona has a lost time of about 20 minutes or something for conduction to get rid of the local radiation and get it down into places where it can radiate. And then the other point is that, when much like almost essentially all the research ever done on the corona, people are looking at what they can measure. And for me, the interesting question is what light you can shed on heating the corona. That's the real issue at hand. And so, these kind of studies, pretty much anything observed with IRAS is always just observing effects, not causes. So for me, it's not a particularly interesting problem what you're doing. And as I said, I'm not trying to be rude or anything, but I would appreciate your ideas on those 2 points.
Thank you, Phil. Thanks for the comments. Thank you for tuning in during your holidays. So
I'm sorry, I was disconnected earlier.
Sorry, Bettina.
Can I still? So you mentioned that there is.
Wait, Bettina. I have a question to answer first.
Yes, please. I'm sorry.
Phil has asked a question. Indeed, the corona, the message that I'm trying to show here is definitely not that the solar corona is thermally unstable, everywhere. But the thing is that it is far more unstable than we have thought before, and in particular in active regions, we see. Of course, there will be differences among active regions. That's an open question, but we see active regions that are raining all the time, and this of course poses a question, right? So the numerical simulations around there have told us, have indicated that it's actually very easy to obtain this kind of thermal non-equilibrium state, but it's also very easy to get rid of it. So you have this very large parameter space. You have so many factors that are playing a role, and yet we see these pulsations, for example, that are extremely periodic, that are happening over a week. So there are a series of observations there that show that this thermally unstable plasma is much more prevalent than previously thought, and that it has and this has consequences for the hot corona. So this is the most interesting part for me. So this is the link that happens, the consequences. So what it implies on the coronal heating mechanisms of having this amount of thermally unstable plasma. Yeah, I guess it's an open question of how much there is still there.
Thank you. Two more questions. A question from Bedzina, and then the last question from Daniela in the chat.
Bedzina, you're muted.
Bedzina?
Oh. Maybe you can go with Daniela first, then.
Yeah. So a question from Daniela in the chat regarding the flare-induced coronal rain. Can you go into more details on what secondary mechanisms have been considered? And are the asymmetries you mentioned referring to asymmetric heating or asymmetries in the structure itself?
So this is a part of an analysis. So this is a study I made with a student of mine. It's not yet published, but we found. So we considered a secondary heating mechanism. So we considered several parameters for this secondary heating mechanism, varying the duration of the heating, the amount of heating, the asymmetry, so basically the amount of heating that is placed at one foot point versus the other foot point. And what we got was that the cases for which we obtain coronal rain are very strange, are cases for which the rain always goes up because of the very strong gas pressure at the foot points. It always goes up instead of going down, and then it basically kind of evaporates. It disappears going up. So nothing that matches the observations. The only case in which we found something that matches the observations, in which we have extreme asymmetric heating between one foot point and the other, almost all the energy on one, like 90% or so, and also is the fact something puzzling is also the fact that we still need very large heating, so compared to a normal coronal loop. So if we have a secondary heating mechanism, then the question is then how it is related to the flare. Is it related at all? It has to be related for that kind of heating. But another perhaps much more plausible explanation is the multidimensional effect. And there you need to consider that above these arcades you have strong reconnection outflows that are constantly perturbing the area, the cross section of these loops. So this every 2.5D simulation will show you that. So in 3D it should be the same. You have this reconnection outflow that is impinging on the loop arcade. You have strong magnetic pressure there, and that may be enough to trigger the thermal instability. So probably that's where the solution lies.
Thank you very much. You also answered my follow-up question, so thank you.
Okay.
Thank you. Thank you. There is so we lost Bedzina again. So now I'm intrigued as to what he wanted to ask, but we don't have him here. So I propose that we conclude the questions and answers session because we are running a little bit over time. But thank you, Patrick, again.
Sure. thank you very much for everybody for tuning in.
Oh,
And have a
Bettina,
he's back.
Bettina.
He's back. Yes. Hello.
Yeah, I'm back again. So I have to, if it's possible, I will ask quickly because I have very bad connection, and that's why I could not catch your point. When you mentioned that you found that the velocity is proportional to the density to the power 0.64, is it a result of the numerical simulations or it is observationally detected?
It's a result of the numerical simulations in 1D and 2D. So that's the contrast, the density contrast between the clump and the environment to the power of 0.64 when for the case of very strong magnetic field. If you have a lower magnetic field values of 5 Gauss or so, you have a deviation of this. And for that case, so where you don't have a magnetic field at all, then you will have actually KHI forming in the wake of the rain. And for that, we know what happens very well. On the analytical side, we can understand the relation between the velocity and the density for that case. Yes.
Okay. Thank you.
And that the power there is 0.5, I think, for the pure HD cases without magnetic field is 0.5. Yeah.
I see. Thank you. Thank you.
Yeah.
Okay. So let's conclude the question and answer session. And thank you, Patrick, again.
Thank you very much, everybody, for joining, and have a nice rest of the day or a good night.
Thank you very much.
Thank you.
Thanks, Patrick.
Thanks,
Thank you.
Bye.